Okay, so in this session, I'm going to try to kind of build on last week and also kind of get into some more, or going to get into dynamic simulations a little bit, specifically the frequency analysis. Based kind of on a little bit of stuff we did last week with the spring connection, I'm going to start with covering another connection that's going to be very helpful as well, which is going to be the pin connection. So I'm going to go ahead and start a new part file here real quick. Kind of do a little bit of work with that, and then try to take maybe the second half of the session and try to do a frequency study with you all. Okay, so I'm just gonna start off sketching here on the front plane. I'm just gonna try to get like I'm gonna try to model like kind of two little links that need to be kind of linked together with a pin, and kind of show how you can kind of set that up in simulation. So the first thing I'll do is I'm just gonna do two slots that are so I'm gonna kind of put a slot like this. And I'm gonna put another slot over here to kind of, obviously, I want to make these the same size because I'm gonna try to link these together. So I'll just gonna make these two here collinear. One thing with slots that's always fun is, a lot of times what will happen is this here will actually select the entire slot. If that happens, you can always just grab the arcs, holding down Control and make them equal. You can just actually do equal slots completely. That should mean, yeah, they'll also scale completely. There we go. So let's put a couple dimensions here. Let's give a radius here of, let's say 0.5 inches. And let's go, and then if I go here, and let's say they're maybe about 5 inches long. Okay. So something like that. And then what we'll do is, let's put some holes here as well. Yeah, typically if you're doing this in real life, if you're trying to make a drawing of this, it's obviously better to use Hole Wizard. Obviously it's a lot better in the drawing for doing hole callouts and things like this, but for doing something quick like this, just using a circle and either doing an extrude cut or just extruding without that region can be very, very quick and useful. So I've got that. I'm going to grab all three of these holes and make them equal. And let's give these a dimension. Let's make it like maybe 1/4 of an inch or something. Or maybe 3/8, 0.375. Okay, so something like this. Then I'm gonna just do a couple series of extrudes here. So go extrude, and I'm gonna try to extrude the first link first. So I'm gonna grab this and this, and I'm gonna extrude it maybe, so what 0.375 looks like. Yeah, 0.375 looks about right. So we'll go ahead and extrude that one direction. Then what I'm going to do is I'm going to extrude this other portion the other direction at a separate feature. Again, this is kind of a very quick way of doing it. If you're trying to get motion or something, it's probably better to do these separate parts and then put them in an assembly. But for simulation, it really doesn't matter too much. And this is kind of a quick way of modeling if you don't really need a lot of assembly functionality. But if you do, then it's better to kind of do them as assembly starting out. So I'm going to do this. You
Well,
probably
assembly
seen.
usually takes longer for simulations, doesn't it?
Yes and no. That is a great question. So for an assembly, it depends. Again, it depends mainly on the contacts. So
Mhm.
in general, I would say typically an assembly will take longer, not necessarily because it's just an assembly, just because usually an assembly has more going
Assembly
on,
has more going on. Okay.
right? Than just
Right.
like a, yeah. I think is there an echo? Uh, I think is it better now? Okay, I was hearing an echo on my side. Yeah, so typically it's not necessarily it's going to take longer just because it's assembly, but if you've got a lot of parts and stuff, especially contacts, one thing with simulation, contact conditions will definitely, especially when you're dealing with contacts like a non-penetration or just a contact condition, for SolidWorks simulation to analyze those can be very long because it has to figure out how every body interacts with every other body or everyone that's touching. So those can definitely be longer. So yeah, when you're dealing with multiple parts, especially with contacts in an assembly, those are usually expected to be the longer types of simulations, if that makes sense. Okay. So what I'll do here, I'm going to do another extrude. And in this case, I'm just going to extrude these two regions there. Again, I'm using selected contours. I'll delete this sketch one, which is the entire sketch. I only really want this portion. And what I'll do is I'll go and flip this the other way. So I talked about this a little bit last time, and then and this is the case where I want to uncheck merge result to keep these as separate bodies. to kind of, because I want these separate bodies, because obviously if they're all merged as one body in simulation. My whole point here is I want to actually try to fix one end here or do something like that and pull this this way, and then hope kind of see and do kind of a pin connection in between the two here and see how that kind of works. So yeah, that's kind of using a little bit of multi-bodies to keep these separate. So I'll go and hit accept there. I'll stop here. Anybody have any questions about, let me go and actually save this part. While I'm saving, does anybody have any questions about kind of anything I did here or anything so far?
No, not really.
Okay, perfect. Okay, so we'll do this.
Uh, sorry, I got cut off with my network. Did you just do an assembly?
No, so this is actually just a part. So this is, so I kind of mentioned this a little bit. So the reason I kind of did it this way, if you want more assembly functionality, obviously an assembly is going to be the way to go. I kind of did this in the part environment just to have two separate bodies. The reason for that's a little bit quicker just to model. But typically, if you're doing something in real life, it would probably be an assembly. Unless it's something very, very simple like this, where you can kind of, there's nothing really wrong with doing it one way or the other. But if you've got a lot of components that you're trying to, kind of mate together, an assembly is definitely going to be the way to go. Or if you have a kind of several components that you want to maybe it's easier just to sketch them in one part where they're kind of connected and everything. You don't really have to do a lot of mate work. It's a little bit easier doing it this way. But doing an assembly study or a study like this should give you very similar results. It shouldn't really affect anything like way too much. But yeah, does that kind of answer your question?
Yeah, cool. Thank you.
Okay. You're
So
welcome.
two
Perfect.
solid bodies.
Yeah, two solid bodies, and then yeah, kind of how I'll do a little bit here. So kind of how I did that is first one, I did one sketch. I extruded this sketch this way. I extruded the same sketch in a separate feature going this way. And I unchecked this merge result, which means even though the bodies are technically touching, they're still going to be separate because obviously I don't just want to have one big block of material. That's kind of how I did that. Okay, so we have this now. Let's go and save here. So now this is a really quick example. Now let's go and jump into simulation. So obviously last week I went over kind of the spring connector, where if you don't want to actually have to model the spring and get the material properties right and everything, that's a very nice way to kind of model that, or not necessarily model it, but have simulation account for it without having to do a lot of modeling and a lot of contact work. So this is what I'm going to do. I'm going to do a similar thing, but I'm going to use what's called a pin connector to kind of connect these two together. So let's go here. Let's go over to simulation, and let's go to a new study. In this case, it's still going to be a static for now. I'll just call this static one. And so in this case, should be very familiar so far. For now, one thing, obviously, if we're dealing with contacts or we're dealing with connectors, since these bodies are touching, the first thing I want to look at or want to disable or want to change is this global interaction here. I don't want these to be bonded because right now by this being bonded, that means this contact area between the two bodies is equivalent to being glued or welded together pretty much, which is not really what I want. So what I'm going to go down here, I'm going to go to the component interactions. I'm going to go to this global interaction. I'm going to edit it, and I can kind of choose one of the two here. I can either choose contact or I can choose free. So obviously contact, like I talked about, I think either last week or the week before, where they can't necessarily penetrate each other, but it will kind of give some more, what's the word? I'll give it a little bit more of a realistic, what's the word? More of a realistic example or a kind of a realization of how it would be in real life. But it can also give you some more simulation time. Free means they're pretty much one can physically like float through the other one. There's no real interaction at all. So in this case, I'll probably do contact, and this is a very simple kind of collection of parts here, or kind of assembly for a study. So I'll do contact. If it takes a long time, I can switch it to free or something. But with free, I'm going to have to do a little bit more work when it comes to actually kind of defining it. Otherwise, these can technically just go right through each other, which would be a little bit of a problem. So I'll do that. So what I'll do here, I'm going to go ahead and hit accept here, just do contact as my global interaction. And so now what I'll do is I'll move on to doing fixtures. So what I'll do here is let's go to a fixture. Let's do fixed geometry. And I'm going to just do a fixed geometry on this cylindrical face here. It's kind of simulating if this was just bolted to something else. Maybe you had something mounted to the wall and you had a bolt going through here. And it's kind of maybe it's a whole length of links in a longer chain. So I'll kind of just fix that there. I'm going to hit accept for that one. But now obviously, so this one is fixed. This component, if we kind of pause here for a second, I kind of look at what we're dealing with. What this fixed constraint does, this face obviously cannot move in X, Y, or Z, and it cannot also rotate. There's no moment about X, Y, or Z either. So which means this can't rotate. So this component right now is fixed. The only thing that would not be, only thing that would be allowed to deform would be the actual body itself. Obviously once a load or something is applied, if that makes sense. So then what I'll do is I'm going to try to obviously have these kind of gone together. Typically what you could do here is you could obviously just do a pin. I could actually do I could just do a body going through here. And actually, I might do that just to show before I get into pin constraint. Just that might be actually a good way of doing it. I'm going to go back to the model real quick, and I'm just going to do a new sketch on this face here, just to kind of show how you would do it if you didn't use connections. And what I'll do here, I'll just do an offset entities, and I'll grab this. I'll do reverse. I'll do like a very, very small offset, maybe 0.01. Something like that. So there's a little bit of a gap. Again, I could go right on diameter as well. It wouldn't really matter too much as long as it's treated as a separate body. But to kind of have a little bit of a gap will kind of show as it deflects, you'll kind of see the gap change from, equal on both sides to mostly on one side or all on one side. So I'll do this, and then I'll just create a little pin here. And so let's do an extrude. And I'm going to go and flip the direction of this extrude. And I'm going to use an end condition here that's called up to surface. This is just a way, obviously, I extruded both of these 3/8 of an inch. So I could just type in 3/4 of an inch, which would be the thickness here. But a very nice tool in the extruder, a lot of features, is just being able to switch the end condition to like either an offset from surface or an up to surface in this case. So I can just select this surface here, and it'll automatically calculate what that distance needs to be. So it'll go from where you're sketching all the way up to that other face. So it's a really quick way if you don't want to have to do a lot of dimensioning work or a lot of calculations. Again, in this case, it's a really simple example, but if you have more complex things, or if this face is even not flat, maybe this face was actually curved, maybe it was a cylindrical face, it would also match that cylindrical profile as well, which is really, really nice. So we have this, again, in this case, the merge result is really not going to change much for this pin because there's physically a gap. I can't merge if there's a gap. One thing though, I don't want it shouldn't technically merge these two together, but just to be safe, I'm going to leave this unchecked. Just kind of how I did it the first time. We'll go ahead and hit accept. Okay, so we have this. Then what I'll do is if we go back to our static analysis, so again, our global interaction, I always switch to contact. So by that being contact, this pin, obviously, when this starts getting pulled apart, this pin is not going to be able to penetrate into these other bodies. So that contact condition will pretty accurately represent this. So let's see. So we've got that. Another thing we can do is, let's see. So we've got that. Next thing I'll do, I'll go and apply a load, and then I'll come back and try to kind of work around with this a little bit in the middle. So let's do a load, and let's just grab a force here. And let's grab a force on this cylindrical face here. Obviously, by default, the force is going to default to a normal to force. So it's almost like if you were putting a pressure, not necessarily a pressure, but you're putting a force that's acting normal to this face at all points. That's really not what I want. I want like a force that's actually pulling these apart, like kind of a tension force going this way. So the way to kind of fix that is you can go, instead of doing a normal to direction, and you can do a selected direction. And for that selected direction, you can pretty much select any kind of reference you want. You can select a face, a plane, an edge. So in this case, I'll just select this face right here. And I think I've talked about this maybe a little bit a while back, but you can kind of just do these different directions here and to kind of figure out which direction you want. In this case, I want this direction here. So I want along, in this case, the X direction. And we'll make this maybe, let's see, maybe 500 newtons or something. Again, I might have to modify this depending on if that's too much or too little, but we'll go ahead and hit accept there. So that's kind of the force. And I'll go and stop here and ask if anybody has any questions here as well so far with any of the modeling or the fixtures or loads. Okay. So kind of moving on. So right now we obviously have this contact. Another thing to kind of look at here is this pin, though, if we're looking at this component, there's nothing really that prevents this link right here from flying out into space this way, or the pin from flying out into space. So we obviously know that when you pull on it, they can't penetrate each other because of the pin. These two can't penetrate, again, because of that global contact interaction. But they can still very easily still move apart. I'll kind of show, I'll try to mesh and run it without doing anything more to kind of show you guys what it'll look like if you kind of get things like this. Sometimes it'll work. Most times it actually will fail because there's just always going to be something that's not constrained. So I'll just create a mesh here, and I'll just kind of leave it in the middle and see kind of what kind of mesh that's going to give me. And that's probably a fine mesh for this example. I've got two elements across, so that's pretty fine for this example. I'll go ahead and run. There's going to probably be the first thing is going to probably throw an error is going to be a large displacement. Again, I don't know if you guys can see the little window that pops up when the simulation is running. I don't think you can, but it's just saying solving right now. And yeah, so it's going to say excessive displacements. And if I go and just say, let's actually not do that. I'm going to terminate the simulation real quick. I selected to run with large displacements. I try to run it again, actually without large displacements. What'll end up happening, it'll either it's still doing large displacements. Let's try this real quick. So if you click large displacements by accident when that window pops up, you're gonna have to go over here to properties and then go to large displacement and turn this off. So we'll go there and then I'll try running it one more time, obviously without the large displacement. And what will end up happening, this simulation will still fail because this pin, either the pin or this component here is just going to probably fly out into space. Because even if you have a very, very small unbalanced force, I'll say no to the, yeah, so then you'll end up with something like this. Obviously, so if you ever have something like this happen, then you know that pretty much in this case, we know that this is not obviously the behavior we're looking for. So then we're going to have to kind of go back to the drawing board with our fixtures and try to kind of play with it a little bit more. But if you see something like that, that kind of is a good indication that your fixtures are not working 100% correctly. So let's go to our fixed constraints. So what I'll try to do here is, let's see. Let's go to our fixed and let's go to, so the first thing I'll do is let me go and hide this stress plot real quick. So let's go here and let's hide. And what I'll do here is the first extra fixture I'm going to put a roller slider on these top faces right here, on both of these here. The reason for this is I just don't want these kind of rotating around. I want this to be in kind of perfect tension. I don't want them kind of being able to roll around. Again, I could put these on both faces here. The thing though, I don't want to put them on both faces because I do actually want to see as I pull this. If any of you remember from your strength of materials class, something that's called the Poisson's ratio. So when you pull on a member, the member will actually, as it stretches in one direction, it'll actually shrink in the other direction. Very similar to how when you stretch on a rubber band, you'll see the cross section actually shrink a little bit. So if I put a roller slider on both of these, that's going to pretty much constrain these faces only on those planes, and it won't actually allow this to actually deform, which is not really what I want. I actually do want to see some deflection in there. Again, in this example, it's probably not going to be a lot, but it's still something to always consider. Again, this is only one way of setting up the simulation. You can kind of set this up, obviously different ways depending on what you're trying to do. Okay, so we have that. So now these are going to be obviously both on the same constraint or on the same face. Pretty much they can't really move apart. But I still have not solved the problem with these moving this way and the pin. So one thing I can do for the pin is I can put a roller slider on the pin as well here. Another thing, this again is a very simple simulation. I don't want to go too advanced with this one because typically I should probably put a, actually I'm going to change one thing here on the simulation before I actually run it. The reason for this is actually be a lot more complicated of simulation. The reason for this is when I pull on here, this is what would be known as a system in single shear, meaning you're only going to shear the pin at only at one place. The problem with that as well is since this is kind of unbalanced, it's going to actually end up flexing one way. You're not pulling this completely straight apart. If you ever tried to pull two things that are offset some distance, you'll probably notice that you end up with a moment that's being generated. And again, you can run a simulation like that, but for this example, I'm more concerned with the kind of the pin constraint. I don't really want to get too advanced into that type of stuff. So I'm going to go and put this, I'm actually going to cancel this fixture real quick, and I'm going to um, kind of go back to the model real quick and just kind of switch a couple things. One thing I will do here is, let's see. I'm going to put a plane right down the middle of this component here. So what I want to do, actually, I'm trying to think if there's an easier way of doing this. Actually, there is an easier way of doing it. I'm going to go back to this extrude real quick. What I'm going to do is I'm going to edit the feature. And instead of doing a blind all in one direction, again, I'm going to, after I'm done with this, you guys might have some questions. So I'm going to stop there and make sure anybody doesn't have any questions about this. Or if anybody does, we'll make sure to answer them. So what I'm going to do is I'm going to switch this to a mid plane. And it's not going to make a lot of sense what I'm doing right now, but in a second, it'll kind of make sense. What I'm doing by doing this is I'm ensuring that a plane is going down the middle of this body here real quick. And what I'm going to do now is when I go to my second extrude here, I'm going to, again, edit the feature. And instead of extruding from the sketch plane, which is on that front plane, I actually want to start extruding from here. So what I want to do is I want to grab this now. Instead of doing from sketch plane, again, very similar to how I did earlier, going up to a surface, you can also start from a certain surface. And I want to start from this surface right here. So I'm pretty much replicating what I had earlier, but keeping this plane of symmetry. What I'm trying to do is I'm trying to set up for a mirror so I can mirror this component about that plane there, or this and vice versa. So what I'll do is this, and then let's go and hit OK. So we've got this plane here. Now what I can do is I can actually, let's see here. I actually did this backwards. I actually did this backwards. Because I actually want two links here. I want one link pulling out. I don't want to have to put forces on two different links. So I'm going to do the same thing, but I'm going to switch this around a little bit. So what I'm going to do is I'm going to go to this one. I'm going to go to edit feature. I'm going to just do from sketch plane. I'm going to do the mid plane on this one. They're going to be on the same thing there. Then what I'm going to do is, one thing you can also do in SolidWorks, this is something that a lot of people don't know, you can actually switch features around. So in this case, since I want two here and one here, I'm going to bring this feature up. The reason for doing this is, I'll get into that in a second, but the reason for doing this is, I obviously want to uncheck merge result here, make sure we're through solid bodies. Reason for doing this is I cannot reference this face if this face was created after this feature was created, if that makes sense. So what I'm going to do here, I'm going to go to here, and I'm going to do a very similar thing that I did earlier. And again, I'm going to stop here in a second because I know I'm kind of going back and forth here a little bit. I'm going to go here, and I'm going to grab that face right there. Okay. So the thing I want to do now, I'll stop here for a second. Does anybody have any questions? I know I kind of went around a little bit.
None of mine.
Okay, perfect. Okay, so, and let me know if anybody has a question, just go and stop me as well. So what I'm going to do now is I'm going to pretty much use this body. I just want to mirror this to the other side. So I want to have two links, and I want to have this coming straight out. Again, this is going to simplify our simulation a bit because then we don't have that moment that we're going to have to try to play with. So that's what I'll kind of want to do. So I'm going to go here, go to mirror. So go to mirror, use our mirror facer plane. This is the reason I did this work with the mid plane and the offset or the up to surface work, because I want this plane to be right down the middle here. Because then what I can do is I can mirror this body to the other side here. Again, if you're not familiar with working with solid bodies, it's a slightly different mirror process than you're used to working with features. You can't just do a features to mirror. You actually have to come down here to bodies to mirror, and then select the body, and then it'll mirror it to the other side. So that's one thing that's a little bit different where you're working with bodies. It's a very, very similar thing besides that, but you just want to make sure if you try to select a feature, it won't actually work very well if you're trying to mirror the body. Okay, so we'll go ahead and go do that real quick. Now we've got four solid bodies. So obviously we've got that component, we've got these two, actually we've got those two, and then the pin. One thing here real quick, again, I'm kind of reorder features again because I want the pin to be last. I want this pin to obviously go all the way through. I don't want the pin to just stop right there. So what I'm going to do here is I'm going to grab this again, and I'm just going to switch the face here. Instead of going extruding up to here, I want to extrude all the way to there. That should be a quick thing, very similar to how I did it earlier. Okay, so let's go and save here real quick. So we kind of modified that a little bit. Now what I'll do is let's go back to our simulation. So there's a couple things we need to modify. Obviously, the mesh needs to be different because, or it needs to be remeshed because we've added different components. We've changed the geometry. The fixed constraint obviously needs to get modified because now I need to fix both of these instead of just one. That's a very easy change. Again, the force is the same. It's still based on that reference right there on that cylindrical face. So now what I can do is, at this point, I really don't have to do much else except put a roller slider on this pin, so this pin just can't slide out of the hole. Because based on the contact condition I have, obviously this cannot just escape now anymore because this is obviously blocking it. When you have a contact, this can't penetrate either side here. So it's all it's able to really do is kind of slide back and forth. So what I'll do here is I'll go to the go to fixtures again. I'll go to roller slider. I'll put a roller slider on this pin here real quick. And we'll do something like that. So now the pin is going to be pretty much with this face here. It's not going to be able to really pop out of the hole like you saw originally. We'll go ahead and hit accept. In this case scenario, we can also, I could go back and put that roller slider on these top faces, but I'm going to try to actually run it without those first because I actually want to see if I put a roller slider here, that's not going to be a very realistic behavior because when you have a linkage like this, like I was saying, kind of with the Poisson's ratio, it's not going to be very realistic for it to not shrink in this direction. You're going to expect to see it kind of shrink in both directions. And the contact conditions in this case should work just fine in that regard. If it doesn't, though, I'll kind of go back and kind of do it. This is where you want to kind of run more of a preliminary study to kind of see, kind of see what the behavior is before you kind of go through and do a really fine mesh and do a really fine study. Okay, so we have this real quick. Let's go and save. Any questions so far? Okay, so moving on now, let's go and just remesh. And so I'll just do a mesh and run in this case. We already have our mesh parameters specified. So go and do a mesh and run and let this study go on and run. And just kind of see what kind of results we're getting. Again, with contacts, this is going to take a little bit of time. Again, contacts, if you can try to reduce contacts, that is usually a good way to go because contacts will make your studies run quite a bit longer. We're at about 20 seconds right now in this study, and we're at about 27.3% complete. So we'll see what happens here. And again, we have excessive displacements. I'm gonna say no. So yeah, so see in this case, this is obviously not the behavior we're looking for. So this is where I'm gonna actually have to go back and put that roller slider or put some sort of constraint to stop this from, obviously going up and down like this. Okay. So what we can do here is let's go here and let's go and hide this stress plot. So this is a very realistic way of how you would do studies. Again, a lot of times this is a situation we'll run into a lot, where as you're trying to set up a study, you may be running into issues like this and you have to kind of go back. So I'm kind of trying to show in this example how you can, like kind of some of the stuff you kind of run into, and if something's not completely fixed properly, you can always check it, and if something just doesn't work properly, then you can kind of go back and kind of adjust different things. So let's go and hide this and kind of keep constraining it. And this is where constraints can obviously be very important. So there's a couple things we can do. We can either put obviously I don't need to put any roller sliders here. I actually made a mistake earlier saying you need a roller slider here. You do not, because of this fixed constraint here. This cannot rotate. So there's no need to put a roller slider here. We can put a roller slider here. That's probably about the simplest way of doing it. Again, you could also do some other constraints on this face here to maybe say it's not deforming in the vertical direction, in the Y direction in this case. But this is more just what I'm really trying to cover here is just the pin constraint and how to kind of work with pins. So I'm just going to go with the roller slider method. It's maybe not the most accurate, but it's good in this. It would be good enough for this example. So we'll go here and put a roller slider right there. Again, I could put a roller slider here or here. I don't really need to put one on both. Like I said earlier, I'll just choose one. So we'll do this and hit accept. So now in this case, this is not going to be able to rotate around. It's only going to be able to slide along this face here. So this face cannot go up and down. It can't, think of this as almost like a wall. This component can't really penetrate that like invisible wall. Sometimes there's another type of constraint. You'll hear people talk about that's called the virtual wall, which is very similar to this. So we'll do this and then I'll do a mesh and run one more time. So what we'll do here is this should run a lot better now that everything is constrained. So we'll go here, do a mesh and run. And we'll see, this should run rather quickly. Usually if your study is taking a long time and it's a very simple study, then that could be that there's an issue. Again, with the contact condition here, it may still take a little while. It might take like 20 seconds or something. We're at about 15 right now. And we're about, let's see, we're running about 20 now. And this is where obviously contact constraints, especially this contact, again, we still have excessive displacement. So let's see how this is moving. The excessive displacement is probably because I put too much force, I'm guessing. I want to see deformed. Yeah, this is an actual. I actually want to see deflection here. Let's go and animate this real quick. And this is another thing. So then I'm going to put another roller slider here. So one thing with SolidWorks simulation that's actually rather odd, I would say, but this is pretty typical for FEA packages, is although from a physical problem that you would think about, like maybe in statics or something like that, when you apply a force here and you're fixed here and you've got all this stuff, you would not think that it would be able to move this way because it really shouldn't be able to move this way. But a lot of times what happens, you have these unbalanced forces. What ends up happening is it starts deflecting and then the force will end up, kind of following that direction. So in this case, again, I'm going to go back and put another roller slider to kind of fix this. So we'll go here and we'll do, let's go back to our roller sliders here real quick. But this is actually a really good example to kind of see kind of some of the stuff you can run into. Like especially when you're setting up a study for the first time, I'm just kind of coming up with this thing off the top of my head. And this is some of the stuff you'll kind of run into, especially when you're dealing with maybe a assembly or something that you haven't really kind of looking at this and you're starting to put fixtures, but you don't really you're not really 100% sure if you're fixing everything properly. You may, when you run it, you might run into some issues like this. A good thing is based on that animated stuff, a very good skill in simulation is to kind of know, based on that, how do I know how to restrain this? So you're trying to figure out a way. Obviously, we don't want this flexing back and forth. One way is to put a roller slider. It's probably one of the simplest ways to do this, while still having the geometry or still having the motion we're looking for. Okay, so we'll hit that. Again, I could have put all three of these in one roller slider technically. I did not have to do three different fixtures here, but it won't hurt to do them separately as well. So we'll go here and then we'll do, now we'll just do run. In this case, I have not changed any geometry, so I don't need to remesh. I can just do run this study real quick. And we'll see. So hopefully this will run a bit quicker now. And while it's running, let me know if anybody has any questions. Okay, so let's see. So we've got yield strength. Obviously, one thing here, we're looking at the whole plot, and most of this is actually just blue. The reason for that is the stress we're actually anticipating is not going to be on the entire plot. The one we're really looking for is in this pin, because this pin is literally getting sheared apart. So you have actually very minimal stress here, and you've got a rather high stress on the pin. Another thing you can also do here is you can also go to your, I think this is another thing you do with separate with different bodies. Let's see under advanced options. Let's see. Yeah. So another thing you can do is under here, especially when you're doing multi-bodies or assemblies, it's really nice to be able to show plot only on selected entities. And in this case, the one I'm really looking at, I really want to look at this pin. Actually, not the pin. I want to do bodies. So this is for faces, this is for bodies. And I want to just show just this pin. So that's a great way to kind of look inside. There are other tools as well for doing this, but this is a great way when you have something that's completely inside, and that's really what you're looking at. Because we're looking at this. These look great, honestly. You've got like really, really low stress on these. It's a really high factor of safety, but the pin is really what's taking the majority of the load here, or really all the load. So we'll go ahead and hit accept. So this is a great way to kind of look at the pin here, and we can kind of see what's going on. Again, it's not a tremendous amount of stress, not as much as I would expect to actually see. So sometimes you want to try to figure out where the high stress is. Another way, let's go here and let's do a definition, and let's do uncheck that so we can kind of see the entire thing. Because we are getting a value of rather high stress. So I want to actually kind of see where that actually is. It could be on one of these interfacing faces as well. Another thing you can do here, you can also do an ISO clipping, which is nice. So I'll show both of these. I'll show a section clipping first. So a section clipping is a great way to kind of go through the model here to kind of see, and you can kind of see where the high stress is. You're seeing a really high stress here, kind of on the inside face there. So it's kind of very similar to a section view when you're modeling, but to kind of go through the part to kind of see some internal stress. That's a great one. The other one that's also really nice is an ISO clipping. So what this will do is I can actually adjust the stress level in this case. Again, I can also do this for displacement. But I can kind of lower it or heighten it, and it'll kind of put the what is it called? Put the areas where that stress or above has occurred. So we can kind of see above this, it's really only a very small area. So in a thing like this we could probably consider as a stress concentration. So in an assembly like this or a system like this, you probably don't have to consider this much or that much. But it's good to know. There's a quick way to kind of narrow in kind of on the areas of higher stress. You can also flip it if you want to see the areas that are good. So you can want to see maybe, so what you could also do is you could kind of do the reverse and say, and this component is not a great one to do this on, but you can kind of see what is below a certain stress. You can do the reverse. This is helpful if you want to kind of see what components are kind of really good and what aren't. So those are a couple of really good tools for doing stuff like this. Any questions so far on this study? Okay. So that's obviously with the contacts. And now in this case, the thing with this study is the pin is really the thing we would be concerned about. So in this case, you would have to do something similar to this. You'd have to do a contact constraints. You'd have to have a physical body if you want to actually analyze the behavior of the pin itself. But for instance, if we're trying to analyze the, what is it called? If we want to analyze just kind of the stress or something on some of these other bodies, we don't really care about the pin. And a lot of times pins, and if you're dealing with bolts or something like that, these are very, very hardened materials. So these can undergo a lot of stress. So it never hurts to kind of run a study like this, but a lot of times, especially with the FED project, when we're dealing with the structure with a lot of pin connections, that's not really, there's probably gonna be either bolted or pins. Those pin connections are not gonna really be the interest of the study. We're more interested in kind of the deflection and stress of other components. So that's where a pin connection can kind of save you some time when you're running a study. So what I'm going to do here real quick is I'm going to kind of run the same study. I'm going to remove this pin out, and I'm going to use a pin connection instead and kind of show how to do that. So what I'm going to do here is I'm going to go back to the model real quick, and I'm going to create a new configuration. Again, I think I might have mentioned this before, but configurations are just pretty much variations of a part. So what you can really do here is you can pretty much make a different variation of part without having to actually save an entirely new part. So in this case, I want to actually delete out this pin, but I want to have another configuration, which is the default, that if I ever want to run another study, like this study that I already ran, I want to still have that geometry there. So the way you do this, you go up here, you right click, you add configuration. I know I'm going a little bit quick on this, so please let me know if you have any questions. And I'm just going to call this no pin. So I'm going to do no pin. I'm going to go back here. I'm going to go to features. And since we're dealing with multi-bodies, another really powerful tool of dealing with a multi-body part is the ability to actually delete bodies. And there's a tool for this. There's a tool that's called delete keep body. you probably don't have this on your toolbar. I've kind of customized my toolbar a little bit. If you don't have this, you can always go up to the search here and make sure you're searching under commands and do delete, keep body. And what you can do is you can actually, if you have a tool, you can search for any tool you want here. If there's a tool that you really want, you can actually just click and drag and actually add it to your toolbar. And you see that little plus icon. If I release, it'll add it to my toolbar. In this case, I already have it, so I don't really need to add this, but that's how you can if you need to. Or you can just obviously search for it and grab it from the search bar or search dialog. So this delete keep body, obviously, as the name implies, you can delete certain bodies or keep certain bodies. In this case, if I was going to keep the bodies, I have to select all three of these when I really only want to get rid of this one. So I'll just delete this body out here. Hit accept. Okay, so now that's pretty much like it never happened. Again, I could try to suppress the feature as well. But again, if you have things that are based on other features, you can kind of run into a problems doing that. With delete keep bodies, when you completely delete the body out, it kind of limits the amount of errors you can get with one feature referencing another, which is really nice. Which is a really nice way of kind of doing it. Again, it's not something you use all the time, but when you have that specific application, it's a great way to do it. Okay, so we have this. Any questions about the configurations or the delete keep body? Okay, so we have that so far. So now what I'm going to do is obviously go back to our static here. Our static, when you have several configurations, is going to tell me everything's going to be grayed out here because this study was based on a different configuration. So what I want to do here, obviously, I want to create a new study. So I'm just going to go up to, let's see if we go here. So I'm going to go here. I'm going to create a new study. I'm just going to call it static 2. And obviously, since I am in my no pin configuration, which you can always figure out based on after your file name, the part in parentheses is the configuration. If it's default, it'll probably just say default, or if you don't have more than one, you may not see something here. Typically, though, you still will see just default. So I'm in the correct configuration, and I'll just go ahead and do static 2. So I'm going to set up a very similar study to the first one. Again, what I'm going to do here is another thing I can actually do that's really nice. I can go to my static 1 real quick, and since I already have a lot of things here, like my forces and stuff, I don't want to have to reapply a lot of those. So you don't necessarily have to copy a study to actually, kind of copy forces and different things. You can actually just literally select your fixtures. In this case, I want to select my fixed geometry, which is on both of these faces here. I want this roller slider, and I also want this roller slider. I'm just holding down Control to select these different ones. I'm going to select those. I also want my force. And what I'm going to do is I'm actually just going to click and drag down to my study 2 or static 2 study. And now if I do that, and if I go to my static 2 study, now if you notice, those have just kind of showed up. So this is a nice quick way if you've already, put stuff and you've modified the geometry maybe slightly, or you want to do a slightly different study. It's a nice quick way to just, copy forces and fixtures and different things like that. I believe we can also, since this is going to come in default as bonded, I'm pretty sure. Yeah, it's going to come in as bonded. I'm curious here. Let's see if we can actually just drag this global bonded here and see hopefully if it'll switch this. Yeah, now it switches it to contact as well. So that works very well. Okay, so now right now, I can go and save here real quick. Obviously, I don't have a pin here, so my contact is really only going to base it between this component and then these two here, or I'll say these bodies. I use the term bodies and components kind of interchangeably. Typically, component is more in an assembly context, where body is more in a part context. But so I should say separate bodies. But if I switch back and forth, I'm kind of they kind of mean similar things. Okay, so what we'll do here is now, obviously, I don't have this pin to kind of constrain anything out. So I'm going to go ahead and try to do what's called a pin connection to kind of base that, kind of pretend like there is a pin there when there really isn't one. But I'll kind of stop here. Does anybody have any questions about copying what I did or kind of doing the configuration or anything like that? Okay. So what I'll do now is under the connections folder here, or connections, it's not necessarily a drop down, it's more of like a folder. I'll go down to my different types of connections. So obviously the difference between a contact and a connection, I think I talked about this last week. A contact is more how different components or bodies interact. Connection is kind of how to connect two different bodies together. And obviously I covered the spring one last time, which is a really useful one. Today I'm going to try to cover the pin one. And then I'll try to get into, for the last portion, try to do a frequency analysis because that's kind of a little bit important as well. So we'll do pin. This is a very, very simple one to set up. So what you can do here is you can literally just, so when we're going here on cylindrical faces or edges, you literally just select the faces that the pin is passing through. You can also, there are also some other options here with retraining ring, no translation. So that means it won't be able to, the pin won't be able to or pretty much they won't be able to translate apart. So pretty much think of it as a pin and it has, kind of a retaining ring on either side here. So that's kind of a nice way to do it, or you can do with no rotation, but most times like with a key, which means it just has like a little notch you've probably seen on gears and different things, which means it won't be able to rotate. And again, in this case, I'm not really dealing with any rotation here, so it really doesn't matter too much. But in this case, I'll just leave it with the retaining rings. Again, it's not really going to matter too much in this study, but you can kind of play with these. It'll kind of also, sometimes you can kind of avoid having to do some other fixtures depending what you do here. That's kind of how you can do this. So for connection type, you also have distributed versus rigid. So this pretty much just means how the pin will actually kind of deform or kind of how stiff it is. So how much it'll actually deflect. So you can kind of do this based on, it's kind of, if you need to. In this case, I'm just doing a rigid pin because in this case, I want to actually see what the displacements and stresses are just on these components. I don't really want to see it in the pin. Again, do not use a pin constraint or a pin connection if you're actually interested in the force, or not the force, the displacement or stress in the pin itself. This is a way to simplify the study. If you don't really care about what the pins are, you're just trying to get that kind of behavior of the system without having to solve a lot of contact conditions. If you're interested in stresses or something in the pin, a pin connection is not going to be your best option. Again, you can include mass and some other things like that. You can also do strength data. You can try to make the pin out of a certain material. Again, I'm not going to worry about too much of that, but that is there if you need it. So let's do that. Okay. So now I'll go ahead and hit accept. And so the pin will look something like this. Again, you can kind of see those kind of retaining rings at the end. So the pin, so it's kind of restraining it on both sides, so these can't slide apart. If you uncheck that, it would just be a regular pin. So this is a very quick way. So you kind of realize, or you kind of, if you guys remember how long that study took originally. What I'm going to do here is I'm also going to, I'm going to remesh obviously, but I'm going to mesh with obviously, I just left it at the default. So I'm going to mesh again. So this is the exact same mesh, looks the same. And now what we'll do is I'll go and run this study and we'll see how long. The other one was taking about, I want to say 25 to 30 seconds to run. Let's try to run this now and kind of see what we're dealing with. And see how, if it's any quicker. So it should be quicker. Yeah, so that one ran in about 5 seconds. So it's about 4 times faster. So when you're trying to do something with a lot of pins, it's a good way to kind of suppress out your pins. Again, if you need to do this in assembly, you wouldn't necessarily need to do a delete bodies. You would just go to the assembly and just suppress out those components, the pin components, and then do a very similar setup to this. So obviously in this case, we still have a very, very high factor of safety. Again, that's just because I'm just picking materials and picking loads. 500 newtons was apparently very, very low for a system like this. But I'll go and stop here again. Anybody have any questions about pin constraints or anything? I know I'm going a little bit fast, so yeah, please let me know. And also please let me know if you want me to slow down at all or if this speed is fine. Because I don't want to go too fast and that people aren't understanding. Okay.
All seems to make sense.
Perfect. Okay, sounds good. And then yeah, let me know if anything doesn't make sense or something, just feel free to stop me. So a very quick way to do this, where you don't, and the thing is, if you're planning on doing a study like this, I didn't even have to model the pin in. I just modeled the pin there just to pretty much kind of show you if you need to do it with a contacts problem, that's how you would do it. If you're doing it as a connections problem like this is kind of how you do it. And again, it depends what your end intent is. What do you want to actually do? Are you actually considering what the pin look or the things of the pin, or are you kind of you want to consider the kind of the more bulk properties of the system? And again, you could a lot of times for the pins, especially in something like this, anybody who's taking strength of materials can probably remember enough to do a pretty quick calculation. You know what the force is. You know the diameter of the pin. You can calculate the surface area or the cross-sectional area of the pin. You know it's in double shear, which means in this case, this pin is going to get sheared in two places, here and here, if the system were to fail. So you can just do a simple stress formula for shear. So you could say the shear stress tau is equal to V over A, V being the shear force. So V in this case would be 500 newtons divided by 2 because it's obviously shearing at two different places. You can do it that way, or you can literally double the area. That's another way of doing it. Either way, and get a very, very quick calculation. You may not have to run literally run a simulation to actually find that out. Especially if you already know the pin parameters or you know whatever, you don't necessarily, if you do a quick calculation and say that this has a really, really high yield strength or really high failure strength, and you do a quick calculation like that, you don't necessarily need to run the entire study. That's kind of another thing is I will mention a lot of times, and I kind of sometimes I sometimes fall into this trap a little bit as well. A lot of times when you're thinking about when you're in SolidWorks and you're kind of designing something or you're trying to analyze something, a lot of times you kind of fall into the thing where you have to, everything needs to be done in SolidWorks simulation. But not everything really has to be done. If it's something simple like this, you don't really need to, if you're trying to just find the shear, you're trying to find the stress in the pin, it's a very simple system like this. You could do something by hand. So this is where knowing how to do those hand calculations from strength of materials and stuff like that really, really comes in handy. You don't necessarily need to go through the thing of running a SolidWorks simulation. Again, there's nothing wrong with running a SolidWorks simulation, but it's kind of, SolidWorks simulation is more of a tool. It's not necessarily like an end all to every kind of situation. So that's why it's always good, never forget how to kind of run those calculations by hand, because a lot of times you may actually want to run those by hand, even using SolidWorks simulation, to actually see, is the stress that SolidWorks simulation is giving you, is that what you would expect? Because again, SolidWorks simulation, it's a very fancy calculator at the end of the day. So when you're looking at that, it can make mistakes. Maybe you set up your fixtures, you think correctly, the behavior looks correct, but maybe the fixtures you set up or the forces or something are not giving you, although the behavior looks correct, the stresses on different components are not realistic. By running a quick calculation by hand, maybe on the stress of the pin or something like that, if you're doing it obviously not as a connections problem, it's a really easy check to kind of figure out, okay, let's see what we're dealing with here. And even something like this, you could figure out the cross-sectional area of a thing here and figure out I have this much force going here. Again, it's not the most accurate thing because obviously the force is applied here, but you could say that the force is, applied evenly along this entire face or something. So it's really easy to do a quick stress calculation. Sigma, in this case, there'd be a normal stress, sigma equals F over A, and see, are we in the ballpark? It might be slight discrepancies, but if you're like 3 times off of what simulation is giving you, then you either want to check your calculations again, or you want to go back and see maybe what I'm doing in simulation is not accurate. So whenever you're using simulations, there's usually 3 things that you want to have correspond when you're either designing a product or trying to have something, trying to make sure your product or device is going to actually work as intended. You want to obviously do hand calculations. You also want to do simulations, and if possible, you want to do physical testing as well. And between all 3, you want to get values from all 3 of those different testing methods or different analysis methods around the same amount. Again, they're not going to be identical because hand calculations versus FEA versus physical testing, they're going to be different. But if they're within a small percentage of each other, then you know that you've obviously analyzed your system correctly. So that's something you always want to do. You don't just want to necessarily rely on simulation solely and say that, oh, if simulation said it's right, then it has to be right. That's not gonna, again, it might work for you most of the time, but you don't want to, risk your entire part or device just on what simulation tells you. Because again, it may look correct, but it's always good to double check. Okay. So we have this. Any questions on this one before I get into? I'll try to take maybe the next 10 minutes, maybe 15, because I know we started a little bit late, to kind of go over a basic frequency analysis to kind of show how that works. But any questions on anything in this model or this simulation, or simulations, I should say? Okay. So what I'm going to do here, I'm going to try to do a frequency analysis, which is a bit different. So I want to kind of go over it because frequency analysis is a bit different than static. So I'm gonna just do a very simple part here. I'm just gonna close. Let's go and save all. I'm gonna close here. I'm just gonna do a very simple part here. Again, you can get much more complex with this. You can obviously combine a frequency analysis with connections and stuff like that as well. I'm just gonna do a top plane here, and this is gonna be kind of similar, kind of a similar frequency analysis to kind of in the building model, kind of how we're looking here. So I'm just gonna do a 1 inch by 1 inch block. And you can also just type in the value there. If anybody has any questions of how, if that doesn't show up for them in SolidWorks, please let me know. I can show that as well. But it's under options. You can actually turn that on if you want to have a numerical input without having to actually dimension after the fact. So we'll go here. I'll just do features. I'll go extrude, and I'll just do blind in this case, and maybe make this like, I don't know, 12 inches or something. Maybe make it something like this to give it a little bit of height. It's a very simple rod like this. Again, I could do a cylindrical rod as well. But I think this kind of gives us kind of the point. Let's go ahead and save this real quick. And I'll just call this, let's call this frequency example or something. Okay, so we'll do that. Okay, so frequency examples. So we've got that, so we'll go ahead and save. So for frequency study, again, it's a little bit different than a regular static study. So when you go under simulation, the first difference when you do a new study, and well, before I get into the study, what I'll try to talk a little bit about what a frequency study does. So what a frequency study does is it pretty much detects anybody who's taken vibrations will kind of know what I'm talking about. I'll try to explain also for those who have not maybe taken vibrations yet. Um, there is something that's called a natural frequency of a system. And in vibrations, this is pretty much the frequency at which if you maybe hit the component, it's also something that's known as a resonant frequency. So if you maybe like a glass, if you kind of tap on a glass or hit a glass with a spoon or something, you'll hear a certain sound. And that sound is caused by a certain vibration. That vibration is the natural frequency that that part or that assembly or whatever will actually vibrate at. When you're designing products, systems, whatever, you do not want your system to vibrate anywhere clear or close to the natural frequency. The reason for this is it's kind of like a swing. When you're pushing somebody on a swing, if you time it just right, the swing will go higher and higher and higher. Very similar in this case, what will happen is if your vibration is very close to the natural frequency, the amplitude of the vibrations, or pretty much how much the displacement is, or pretty much the amplitude is pretty much how much it vibrates distance-wise, will keep increasing. It might start small and then it'll go bigger and bigger and bigger and bigger and bigger until the entire system or component will just rip itself apart. If you've ever seen people shattering glass with sound, this is what happens. You'll see it vibrate. They're actually vibrating it at very close to its natural frequency, or at the natural frequency. And what'll happen is over time, because it's the natural frequency, when you're vibrating it at that specific frequency, the amplitude will grow and grow and grow and grow. As the amplitude grows, the displacement grows, obviously, which means the stress is increased and increased and increased until the stress will exceed the failure stress of the part or the material and cause the component to fail. So when you're dealing with things you do not want to, what is it called? You do not want to be anywhere close to natural frequency. So a frequency analysis in SolidWorks simulation pretty much is a tool for determining the natural frequency or frequencies of a certain component or what is it called? Component or system or assembly. Obviously, assemblies will, if you have multi-degree of freedom systems, meaning you have maybe many pin connections or stuff like that, you can end up having, you may not just have, you're not going to have just one natural frequency. You might have 5, 10, 15, 100, 200. You may have tons. So I'll kind of get into that when I get into the simulation itself. But yeah, definitely resonance is a problem, especially when you're dealing with vibrating systems, which you probably, if anybody's taken vibrations, they've probably learned. You've probably also seen the very classic example of this type of failure was the Tacoma Narrows Bridge. I think it was in, I believe, Washington State. I think it was. If you can look it up on YouTube, where the bridge, the wind happened to be blowing or something, or maybe gusts at the resonant frequency or one of the resonant frequencies of the bridge. And the amplitude of vibration kept growing and growing and growing until the entire bridge pretty much tore itself apart. So
Yeah,
these can
Dr.
have
Nassiri actually showed us that one in her class.
right. Yeah. So that's definitely, so if you've taken her class for that, you could definitely, you can, if you've seen that example, you definitely know why resonance is so bad. Um, so you definitely, as an engineer, you don't want to be anywhere close to resonance, unless you want to break something, then resonance is great. But typically we want our products and devices to actually not break. So yeah, so that's a really classic example to kind of look at. So for frequency analysis, the first thing you do, obviously, you go to a new study. We're not going to do static here. We're going to do a frequency. So that's kind of the first thing that's different. So we'll go to frequency and we'll just hit accept. There's really, in this case, it's very, very similar to any other study. Our simulation tree looks very similar. There's really nothing that's really completely different. One thing I will mention, I'll stop right here and mention, one thing that's a little bit odd, and this was kind of odd when I started doing frequency analysis too, is a frequency analysis, you do not actually have to specify a load. You need to fix your model, but you don't need to specify a load. You can if your component is under a load, you obviously want to specify it. But if your component is maybe just sitting on a table or maybe it's a glass, there may not be any there may not be any load on that component or part. So a frequency analysis does not necessarily need a load. The frequency analysis is really not going to tell you what the amplitude is. It's going to tell you what the frequencies are. So it's going to tell you those frequencies that you want to be careful of. So a component like this, what I'll do, I'm going to pretend this is like a very simplified skyscraper building or something. Or maybe it's a pencil or some sort of rod that maybe is, I don't know, it's just something, it's a sensor or something, maybe like an antenna. Yeah, it could be like an antenna on a car or something. It looks like a very basic antenna, but maybe this is fixed at the bottom. So I'll do a fixed geometry and I will do a fixed geometry right there and hit accept. Obviously, I believe this is made of plain carbon steel. I can switch the material, obviously, but in this example, I don't really need to do anything. That material is fine to kind of demonstrate what the frequencies will be. So maybe this is like an antenna, and you want to, obviously, this antenna is going to also especially when you're dealing, this is getting into more of a dynamic analysis, which a lot of times you'll have to do, especially we're going to have to do this in the damping project with the building, because we want to actually figure out the displacements and stuff, and a dynamic analysis is kind of how you would do that. But when you do a dynamic analysis, you want to kind of pick a certain frequency. So if you want to pick a frequency near one of the resonant frequencies to see how it behaves at a resonance or at resonance, you want to do a frequency analysis first to kind of figure out where your resonant frequencies are. So in this case, when you're dealing with a frequency analysis, one of the first things you can look at if you go under properties is you have a number of frequencies. So this is a little bit different than a normal static analysis. I'm only really going to worry about this top option right here. So the number of frequencies, well, I'll maybe talk about most of these. Number of frequencies is pretty much how many resonant frequencies you want it to calculate. So what it'll keep doing is it's going to keep increasing the vibration in hertz until it kind of figures out where those resonant frequencies are, or resonant frequencies. A lot in vibrations, these are called a natural frequency, or designated as omega sub n, lowercase omega. So it's going to calculate the number of natural frequencies that you select here. So if you do 5 natural frequencies, it'll calculate 5 for you. If you do 10, it'll calculate 10. It'll just keep increasing the vibration until it kind of calculates all of these natural frequencies. So usually 5 is default. I'll leave this at 5 for now. Again, you can also do an upper bound frequency. Maybe if you know that your system is not going to exhibit any more than maybe, I don't know, 100 hertz, 200 hertz of, that's the frequency of vibration. You can set that there and it'll calculate all of the frequencies up until that point pretty much. So that's kind of one thing that's different about a frequency analysis. You really don't have to really worry about these too much unless you want to calculate more frequencies or less frequencies or something like that. So what I'll do here is I will hit OK, and I'll go ahead and do, in this case, I'm not going to even apply a load in this case. I could apply a load, but there's really no point. So in this case, all you really have to do is, I have it fixed at the bottom. In the simple case, all you have to really do is just do a mesh and run. So it's a very simple study to set up. One thing I actually will mention before I go into mesh and run is, so for connections, for a frequency analysis, you cannot use, if you notice here, there are some connections that you cannot actually use. Bolt is one of them. I think there are some other ones too. You can look back in the recording and actually tell exactly which ones, compare them side by side. But there are some that are not supported. So that's something to keep in mind when you're doing, this also goes for other dynamic analyses. So be careful if you're doing a certain system, keep that in mind, that certain ones, figure out which ones are not going to be supported, and then kind of figure out a way to kind of constrain that in a different way if you need to do a constraint like that. Another thing is when you go into contacts, for dynamic analysis or what is it called, or different interactions. If I do, let's say, a component interaction, obviously I only have one component here. If you notice here, I only have bonded and free. So I can treat them being bonded together. I can treat them completely being free, but I cannot do a contact condition here. So doing a contact analysis with dynamics or frequency analysis or dynamics is going to be not really allowed or not really supported. A lot of stuff we're going to be doing later, and I'll try to probably maybe get into this next week, is starting getting into more dynamic analysis. Obviously, most of the dynamic analysis we're going to be doing is going to be what's called a linear dynamic analysis. I think I talked about linear a while ago, where you have linear materials, stuff like that. So for a linear dynamic analysis, you're not going to have a contact condition either. If you want to compute a contact condition or calculate a contact condition, you're going to have to do a nonlinear dynamic analysis, which just adds an extra level of complexity to your analyses. So if you can get away without having to do a nonlinear, that would probably be a good idea, because then those studies are going to take a long time, because now it's figuring out how everything deforms and how everything contacts. It's going to take a lot longer. So if you can get away without doing contact conditions, that's ideal. So obviously I don't need to do a component interaction here. So that's pretty much it for interactions. Then let's go and mesh and run this real quick, because I want to get into the results. I know I don't have a lot of time left, so I want to try to do a mesh and run here real quick. I'll just use the default mesh, because the results are kind of important. So the results here look very different than what you would kind of see in kind of normal, like a normal stress plot or displacement plot. You're seeing this in terms of amplitude. So just because you have an amplitude here, this does not mean that this is deflecting 1.6 whatever units. You notice there are no units here. This is just pretty much computing, like it's almost like a resultant amplitude, or it's like if you had, let's say, if this let's say if the displacement was 1 millimeter, this amplitude would be 1.6 times that, type of thing like that. So this is not a study that's going to tell you how much your part is displacing. It's more of a thing of the natural frequencies. So one thing here that's really nice, you can do animate. One thing when you're looking at this, you've got your different, obviously we asked for 5 frequencies, it's giving us 5 different plots. So what we're going to look at here is it also tell you the hertz. So in this case, this specific mode shape, which is what they're called, different modes of vibration, occurs at 228 hertz. I would like to do this. I like to always animate these to actually kind of see kind of how this kind of is kind of going on the corner. So kind of seeing how, another thing, a lot of times stop this and up the frames to like 15, so it's a little bit smoother of a plot. So you can kind of see how it's behaving, which is really nice. You can do this for all of your different plots. So you can do that for this one. I'll try to just go through and kind of animate these. It's very similar, but it's going the other corners. It's going kind of at a diagonal that way. So you kind of go through these, and it's obviously telling you that one occurs at 228 hertz. We'll go and animate this as well. So this is kind of a very useful tool. Now you're kind of getting almost like kind of a more of a, you're going to see almost like one period of a sinusoidal function or sinusoidal function, kind of as it vibrates. This one occurs at 1300 hertz, almost 1390 hertz actually. And this one, if we animate. So again, this is very useful to kind of see what the behavior will look like, but also it's very important to see what your natural frequencies are. Again, I only computed 5, so there's probably a lot more than if I go and animate this as well. So this is like, now some of these I wouldn't expect it to be deflecting this way, but you know, some of these again, you can also, kind of disregard to kind of see what's going on. I don't expect it to be expanding out like this. So if you're seeing something like this, then you might want to kind of check your kind of check your study and just see what's going on. So that's a very useful tool. Another way to kind of summarize all of this is you can go to results, and there is a couple different options here. You can list the amplitude. You can also list the resonant frequency. I usually use these two. So list resonant frequencies is a very nice one. So this will tell you your different mode shapes, and it'll tell you what the frequency is in radians per second, hertz, and it'll also tell you the period of the vibration. This is a very nice one, so you can kind of see these are your resonant frequencies pretty much. Again, in this case, since it can kind of vibrate in two different directions, you're seeing it has a resonant frequency in two different kind of directions. So this is a nice one for this. Again, this is a very, very simple example, so this may not be the most accurate, frequency analysis ever, but it's a very good example for kind of seeing how to set these up and kind of looking at your things. Again, I could go back and generate maybe 10 mode shapes, but again, most of these vibrations or most of the natural frequencies are very, very high frequency vibrations. Like 228 hertz is pretty high. I mean, it's not super, super high frequency, but it's not like, like earthquakes, for example. I think the research we were doing was I think it's about somewhere between 20 and 40 hertz, I think it is for earthquakes. So 228 hertz is definitely a higher frequency vibration. The other one that I really like to look at is the list mass participation. This is a great plot or a great table here. So what this will say here is how much mass of the system is actually participating in this vibration. Because you might have a resonant frequency and the system is vibrating at it, but if a tiny, tiny portion of the mass is vibrating, the rest of the mass or the rest of the system can probably damp that vibration out, or it can fight that vibration. So if it's a tiny little bit of the mass, you may not be as concerned, but if you have a large portion of the mass that's vibrating in a certain mode, then you want to kind of be kind of cognizant of that. So when you're looking here, obviously we're looking X, so X is this way, Z is kind of in and out on the page, Y is up. So obviously in the Y direction, we're not really seeing a lot. So one thing you want to look for here, and this tells you if you've done a rather good frequency analysis or not, or if you need to list more frequencies. When it's summed up all these mass participations, these are percentages, by the way, they're just in decimal format. You want to make sure that the sum in any direction that you're interested in, again, a lot of times in this case, we're not really interested in the Y. We're interested in probably the other direction because it's fixed in that direction anyway. But if you were, then you would want to consider that. You want to make sure that the sum of these mass participations, the sum of these percentages, is at least 0.8 or higher. So pretty much meaning all of these combined constitutes 80% of the mass vibrating between all of these summed up. Otherwise, if you have a very small percentage, if you only have like 10% in a certain direction, that means there's still another 90% that could vibrate in some mode, but you don't know what that mode is, if that makes sense. So if this is below 0.8, any of these, you're going to want to maybe switch this to maybe 10 frequencies or something like that, add more frequencies, and these values should go up. Again, if it's in a direction, maybe the Y direction, maybe we're not really concerned about it, then you probably may not need to really care about that too much. But if you're concerned about the Y direction, then yeah, add some more frequencies. Obviously, that is done like kind of how I showed earlier by going into the kind of the frequency plot, or not the frequency plot, the frequency properties, the study properties, and changing that. But out of this, what you want to look at here is obviously the X and Z directions, we have a good amount of mass participation. The next thing to look at is which one of the modes has the most, or which mode or modes has a lot of mass participation. Obviously, in the X direction, mode 1 is what we would call dominant. It's got 42% of the mass participating, where the next highest is 18%, and then like 4%, and then like 15%. So definitely you're going to want to look at the ones that have a lot of mass participation in a certain direction. You definitely want to look at. Same idea for Z. So we've got one that's 42%. So it's kind of a reverse of kind of the X direction, because as you're seeing, you can kind of, since it's kind of a symmetric part, it can kind of vibrate the same way in two different directions. So these are kind of things you want to look at, and based on these, this can really help a lot when you want to go and set up a dynamic analysis to figure out what frequency to kind of pick if you want to see what the resonance looks like, and kind of what things you're getting, or if you want to see if it approaches resonance, or if you just want to be way far away from resonance, you can kind of pick different frequencies kind of in there, especially, and this is also helpful when you're testing a product. If you're testing any of accelerometers or something, maybe you're testing a component in a car, or maybe it's something in a machine, maybe it's a rotating machine with some sort of rotating shaft. It's good to know what frequency of vibration is going to be exerted on this part, and see if that frequency is close to any of these frequencies. Then you may want to stiffen this part, or maybe make it less stiff, to try to adjust these frequencies to get them further away from that vibration that's going to be exhibited in the system, if that makes sense. I'm going to stop here for any questions, and then I'm probably going to wrap up after this if anybody doesn't have any questions about this. But this is kind of a good overview of a frequency analysis. Any questions?
No, I think that pretty much covers frequencies.
Okay. Think someone else?
In a practical sense, that amperes graph on the side right there,
Mhm.
based on those results right now, how would you interpret that, like from a design standpoint? So, like you said, this was like 1 by 1, like it's
Right.
like a 1 inch by 1 inch.
Yeah.
So in this case, you would have to stiffen up by like let's try it 1.25 or 1.5 inches, and
Right.
that's where you would like just try to slowly work your way up to where the whole part would be blue per
So
se,
not
like
not
in the
necess
simulation, but.
not necessarily. Not let me trying to. Of course, my window just went away. Let me try to do this real quick. I'm gonna have to stop sharing real quick, because this is one thing I have actually noticed with SolidWorks. When you have that, oh, there we go. There's my plot. And actually, you can see my plot, right? Or yeah, you can see it. Okay, perfect.
Yeah, yeah. I can see.
Yeah. So this plot, make sure you don't just click on the screen. Make sure you close the plot, because when you click on the screen, it goes in the background, and then everything else in SolidWorks is frozen. So you run into that problem. Just get used to kind of closing this. To kind of answer your question, so no matter how much you stiffen this, you're not going to make the whole thing blue. This is really not a good measure of how, what is it called? This is not really telling you how much it's going to deform. So this is very different from an actual displacement. So this is just the amplitude of the vibrations. This is not going to really tell you anything about displacement or the displacement of the system. You would have to still do a dynamic analysis to figure that out. So the main thing that you would want to get out of a frequency analysis, if you want to stiffen something, you would want to let's say if you're doing physical testing or something, and you figure out maybe the vibration that this thing is going to be exerted to is maybe, I don't know, maybe it's 200 hertz or something, and let's say it's 230 hertz, and we say this mode shape 1 is really kind of close to that, or a little bit too close in that case. Then you could either make it thinner, bigger, whatever, to try to stiffen it or not stiffen it, and that would actually adjust this frequency either up or down depending on what you do. So it's not necessarily so this is really not, how do I put this? This is not really something you want to base a lot of stuff on. This is just kind of, when you're kind of looking at the result, it's kind of, when it's giving you the animation, it's just kind of showing you which part is going to displace more than other parts. But it's not really, this is not going to be representative of anything in real life technically, if that kind of makes sense. I hope that answers your question. And let me know if
Is
it
it based
doesn't.
off a scale? Yeah, it does answer, but is it like based off a scale or something?
Pretty much. So it's based on, again, I'm trying to think, I would have to do a little bit more research as well and figure out exactly how they calculate this. So it's based on, yeah, like a scale. Like if we go down some of those have the same. You can kind of see how some more have more displacement. So obviously, I think it's pretty much, it's like a scale. It's a way of scaling it. So obviously, a higher amplitude would probably equate, when you do a dynamic analysis, if you did it at a certain thing, would equate to a larger displacement. But the two are not necessarily completely 100% related to each other. So it's kind of a way, it's a way of kind of seeing what the amplitude will be, but that's why there are no units here. It's not giving it, so it is kind of like a scale, like if you had one that has an amplitude of 1 and you had another vibration that had an amplitude of 2, you could probably say that, yeah, the amplitude on the second one is going to be double the first one or something like that. But again, it's not going to tell you exactly in real life how much it is. It could be the first vibration is I don't know, it has a displacement when you do your dynamic analysis of like, I don't know, 1,000th of a millimeter, and the second one is 2,000th of a millimeter. So just because it's double the amplitude doesn't necessarily mean that it's like a huge displacement or something like that, if that makes sense.
Gotcha. Okay. Thank you.
You're welcome. So hopefully anybody, and you have any other questions about that, or does anybody else have any questions? Okay. So I think that's probably a good place to kind of wrap up today. So I'm going to save this and let me go ahead and stop recording here real quick.